computer. All right. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, October 24, 2025. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cool and cloudy autumn evening here in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage, inform, and inspire people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has fostered throughout space and time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, myriad Earth and space scientists, educators, and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, we will hear from Ted Blank, whose presentation is provocatively entitled Silent Sky: Henrietta Leavitt's Quest to Measure the Universe. Ted has been a NASA Solar System ambassador since 2010, communicating the excitement of NASA's space exploration missions and discoveries to people in his community and aboard cruise ships. He is a past president of the New Hampshire Astronomical Society and a sought-after speaker who enjoys sharing his knowledge on any topic related to astronomy and the solar system. Ted bought his first telescope in 2007 and still frequently sets it up on the sidewalk to share its views with the public. Ted is a retired IT professional, having spent more than 35 years as a performance analyst with IBM and Oracle. He currently lives in Fountain Hills, Arizona with his wife, Peggy. In this presentation, in his presentation this evening, Ted will share the story of Henrietta Leavitt, who worked in the 1920s at Harvard College Observatory, analyzing variable stars, and whose key discovery allowed us, for the first time, to appreciate the vast size of the universe. Miss Leavitt is also honored in a play, Silent Sky, and a new book, Attention is Discovery, by acclaimed author and artist Anna von Mertens. So let's get going. The Zoom platform is all yours, Ted.
Thank you, Bill, and hello, everyone. Nice to see all the familiar faces and new faces tonight. I'll just mention that I found out about the book about Henrietta Leavitt, the most recent one, Attention is Discovery by Anna von Mertens, when we were back east a couple of years ago, and she was doing an author talk on the book in Peterborough at a famous bookstore over there, something to do with a frog, I think.
Hmm.
And she was there giving readings from the book and autographing copies of it. So we got to meet her and ask her a few questions as well. So that's a really nice book, and I'll show a picture of it at the end of my talk here. I'll share my screen. Hopefully you can all see this okay. As I mentioned, I call this presentation Silent Sky because let me just try to move this off the screen here so it doesn't share. There we are. We'll put this over here. So I call this Silent Sky because Henrietta Leavitt sadly lost her hearing later in life, and the title of the play, Silent Sky, it's really quite a good play by Lauren Gunderson. We actually saw it here in Tempe at the Arizona Theater. And if it ever comes to your neighborhood, I would encourage you to try to catch it because it actually does a very good job of describing Henrietta Leavitt's activities and her excitement about her discoveries and the science behind them as well. So it's actually a pretty good play for those of us who are geeky enough to want to appreciate the actual science behind it. So tonight we're going to talk about this question of how far away are the stars. It's been a challenge since people started looking up, wondering how far away the stars were. And as you all know, when you look at the sky, all the stars appear to be the same distance away on the imaginary thing we call the celestial sphere. The Here's a picture of the list of the nine brightest stars in the sky in order of brightness. And so if we were lucky, we would be able to use brightness as an indicator of distance. That would really make life easy. Unfortunately, that is not the case. As you can see here, the list of the stars' distances don't have anything to do with their brightnesses. And this is a function of the fact that stars can be different sizes and different brightnesses, and as it turns out, different distances. So a really bright star very far away can appear from Earth to be extremely dim. And so brightness doesn't help us with the question answer the question, how far away are the individual stars and how far away are they from us and how far away are they from each other as well. So here's a little painting of our galaxy. You can see that our solar system is somewhere halfway out from the middle in the Orion Arm. All the stars that you see in the sky naked eye are probably within that little red circle or something much smaller than that. I like to use the analogy that if the Milky Way was the size of a basketball court, kind of floating 6 inches above the floor and maybe a couple of inches thick, all the stars that you could see naked eye would be within the volume of a basketball sitting on the floor.
Hmm.
Everything beyond that distance merges into the background of the billions and billions of stars in the Milky Way. So the distance is a big challenge, and it's been a big challenge to astronomers for many, many hundreds of years. And it turns out that in the sky there are these cloudy things that were always called nebulas. Nebulae, the Latin word for cloud, little fuzzy objects. Well, what are they? And one of the big questions was whether these fuzzy objects were clouds of stars or clouds of other material in the Milky Way. Uh, in our universe, was the Milky Way the whole universe, or were they far away from the Milky Way, what people called island universes, or today we would know them as independent galaxies or independent clusters of stars outside the Milky Way, uh, far away. But again, it's very difficult to determine which of those is the case. Um, as I mentioned, our solar system, was thought to be the center of the universe for many years. And if you look at the sky over the course of the night and the course of the year, it does appear that we are the center of the universe. All the stars do appear to go around us. The sun appears to go around us. The moon actually does go around us. But of course, there are those planets that, as it turns out, sometimes go in one direction and occasionally stop and turn around and go backwards for a while and then go forward again. So they muck up the gears and kind of make it difficult to accept the theory that we're actually the center of the whole universe. So are we in the center of the universe? Are we far away? Are these fuzzy objects, the Magellanic clouds that are visible down in the southern hemisphere, are they here in the Milky Way or are they outside the Milky Way? And if they're outside, how far away are they? The Andromeda Nebula, how far away is that? Is it a cloud of starry materials in our Milky Way because the Milky Way is the entire universe, or is it an island universe, a twin of the Milky Way somewhere else? And if it is, well, what good is that big empty distance in between us and that faraway object? Uh, why would it have been put there? What good is it? So these problems are challenging scientists all the time. Oh, one way to determine if a star is close or far away from us is called stellar parallax, and this is works for stars that are very close to us. And you can see in this animation here that when we are on the right side of the sun in this little picture in June, if a star was very close to us, then against the background stars that were really far away, that star would appear to be in one position that you can see marked with a red arrow, just outside, in this case, the Big Dipper. But 6 months later, when Earth has on the other side of the sun, in January, we'd be seeing that star move slightly against the background stars because our angle of view of that star would cause it to shift slightly. That would be called a parallax shift. This only works for stars that are really close to us, and until I think the late 1800s, it was impossible to measure stellar parallax accurately enough to actually prove that stars that were close enough to us did move side to side, tiny amounts as Earth went back and forth around the sun. It does prove that some stars are closer than others, but it does require some very delicate measurements in order to prove that. Um, Not surprisingly, the Andromeda Nebula and the Magellanic Clouds showed no parallax shift, although they weren't individual stars, so that was hard to see. But as best we could tell, no parallax shift for them. So either they're far away or it's just really hard to measure their parallax. Um, so now let's move closer to your homes, the Harvard College Observatory, right? They've had telescopes in both hemispheres since the late 1800s, and they exposed glass plates, and then those plates were developed and placed into wooden boxes with sawdust and shipped around the Horn and up the east coast of South America and of America to Boston, and eventually they were unpacked and delivered to the observatory, where there are now over 500,000 glass plates in the Harvard plate stacks, and that's only through 1993. I was lucky enough to visit the plate stacks back when Allison Doan, who has now passed away, was the curator, and that's because I knew this guy, David Slisky. I met David when he was doing a summer internship on Nantucket Island. And I think Mark might have been with us. We went down to Nantucket to do a star party for some Girl Scouts, and we got a tour of the Maria Mitchell Observatory. And David was there, and so he eventually invited us up to Boston to the Harvard College Observatory, showed me the plate stacks, and I actually got a chance to look at some of Henrietta Leavitt's notebooks, and you'll see pictures of those later on. So these plates are in paper envelopes, and on the outside of the envelope is the information about the exposure time, the object, the right ascension, declination, and so on, and the date that it was taken, and all the information that you need. Um, so here's a photograph of what we called in those days Pickering's harem. So Pickering was the Harvard College Observatory director, and he got mad at one of the folks who was doing calculations and star measurements, a guy, and he said, "My housekeeper could do a better job than you." And so he hired his housekeeper, and she did a great job. And so he ended up hiring mostly women for these tasks, and one of them was Henrietta Leavitt. Another one in the upper picture was Annie Jump Cannon, who's famously associated with stellar color plate the analysis of stars using their color. But Henrietta Leavitt was assigned to work on something called variable stars. She was born in 1868. She did get her BA degree from Radcliffe, which was a women's college in those days, and went to work for Pickering in 1895. She made it into the permanent staff in 1902, and she was a variable star fiend. This is a picture, kind of a posed picture of the ladies doing their analysis of these glass plates, and you can see there's no artificial light source here. They were using sunlight coming in the window to bounce off a mirror and illuminate these transparent glass plates. And they worked long hours, and they were paid fairly well for the work they were doing. How do you do this work? Well, you look at these little dots on the glass plate, and you make these marks in red China pencil on the back of the plate, identifying the various stars and photographing those stars periodically and writing down their apparent brightness compared to other stars on the plate that don't change, and making notes and graphs of the stars whose brightness changes over time. And that's how you study variable stars. Um, Now, in the middle of her work studying variable stars, she was pulled off and asked to do an analysis of stars in the North Polar region around Polaris, and to identify those stars as standard candles so that they could be used to assess the brightness of other variable stars in different parts of the sky. She spent 10 years doing this and finally got that work published. And then she was eventually able to go back to the variable star work that she really loved the most. But These women were not allowed to decide which projects they were going to work on. They worked on whatever Pickering told them to work on, and then they worked on something else that he told them to work on. Here's a picture of the 1911 meeting of the American Association of Variable Star Observers, and there, right in the middle of the front row, sitting down, is our Henrietta Swan Leavitt, along with lots of other uh, famous names, and Charles Pickering in the middle in the background. So this was her assignment, to identify and measure variable stars in the Magellanic Clouds, visible only in the southern hemisphere, but beautiful, beautiful objects. When I went for the very first time to South Africa to do work on a study attempting to catch an occultation of a Kuiper Belt object that the New Horizons mission was heading for, I brought down a whole bunch of star maps because I wanted to make sure I could find the Magellanic Clouds in the sky. And the first time I got out of the car at night and looked up, I threw the papers away. They're like spotlights up there in the sky. They're as bright as could be, at least in the month I was there. And beautiful, beautiful objects. So here's a little Wikipedia picture of them. They're dwarf galaxies, and they're just outside the Milky Way, but they're fairly compact. And so one could assume that the stars in each of these clouds are approximately the same distance away from us. And this was key to the work that Henrietta Leavitt eventually did. So what's a variable star? Well, it's simply a star whose light output, as seen from Earth, varies over time, its apparent brightness. That period of variability could be days, hours, weeks, years, or even decades. And the longer the period, the more difficult it is to develop a detailed graph of the star's variability and brightness, because the points that you get are random points in a very long cycle. So here's a graph of the brightness reported for the star Mira over 3 years from members of the AAVSO. And you can see this is a fairly well-behaved star, and lots of people report their data, comparing it to stars that are not variable nearby, and you can see it's quite accurate. Um, but here's some data reported for Betelgeuse over a period of 3 years. And as you know, Betelgeuse is a star that we're not quite sure what's going on. Is it pulsating? Is it ready to explode? Does it have a companion that's going in front of it that's messing up with its intrinsic variability? Um, so lots of people measure Betelgeuse, and the green graph here represents the best fit curve for these measurements. Betelgeuse is a mess compared to Mira, but it's an interesting star, obviously, to study as well. And here's Delta Cephei. It has a 10-day period, and you can find it easily in the sky. Look for Cepheus, and then you can see Zeta, the corner star, Epsilon near it, and Delta Cephei just below that. So you can actually monitor this star, and a 10-day cycle is quite easy to if you're gonna try to draw a graph like this. Delta Cephei, if it's in the sky, is a good candidate for doing that. Um, so you're all aware of our backwards visual magnitude scale, right? Where the number gets bigger and the star gets dimmer. Thanks to Hipparchus, who kind of decided that the brightest star in the sky should be star number one, and the dimmest star you could see would be star number six. That made sense, number one being the best. But unfortunately, as Galileo came along and invented the telescope and then started looking at stars that were dimmer, we got magnitudes higher than six for the stars that were dimmer than six. So it's all backwards, and folks who I talk to on cruise ships are not as aware of all of this as the folks on this talk. So I always mention that this is backwards. The magnitude scale is difficult to grasp if you're used to, big numbers being brighter things. So remember that it's upside down, and that the higher the number, the dimmer the star appears to us. Um, this is the telescope that took most of the photographs that Henrietta Leavitt looked at. It's a 24-inch refractor, the Bruce telescope in Arequipa, and Harvard has had telescopes down there since the 1800s, taking these photographs. And there was a project a couple of years ago. I guess the Harvard College Observatory actually sponsored this project, and I got to take one of the notebooks from Arequipa from the Bruce telescope home and type in an entire notebook full of data into a spreadsheet. I did it twice and then compared all the numbers, wrote some software on my own to make sure that everything was right, and then sent it all back. So and now that project is taken over by the Smithsonian. So there are data entry folks who are interested in, if you're interested in doing this kind of work, entering data from paper or photographs of images of ancient notebooks, the Smithsonian has a project for you to participate in. So here, as I said, I was able to take a look at some of Henrietta Leavitt's notebooks. Here's one where she looked at the Large Magellanic Cloud, is notebook number 16, and you can see her handwriting and her initials in the lower right, HSL, variable stars in the nebulous regions, large and small Magellanic clouds. She had beautiful handwriting. I got to say, it looks like my mom's handwriting, which was absolutely perfect. And this is how you made your records. Doing this kind of work requires an orderly approach to your job. Every star has to be tracked over time, carefully noted so that you can find it again, write down the information about it. And some of these photographs, these plates, she would have actual paper photographs taken from the plates, exposures, and then cut out those paper photographs and tape them into her notebooks and identify various variable stars in her notebook so that on a next exposure from some weeks or months later or years later, she could find the same star again and compare its brightness and see if it was varying over time. This is painstaking work, and I'm amazed at how difficult it seems and how well she did it. Um, so this is how you study variable stars. You take multiple exposures over time of the same part of the sky. This is how Clyde Tombaugh discovered Pluto. And you compare the stars between exposures. But as far as I know, she did not use a blink comparator. A blink comparator is great for looking for things that move, but it's not so great for looking at things that change in size. That's a very small change. So you build up this list and you assess the magnitude change based upon other stars nearby that don't vary. And of course, you have to make sure that those other stars aren't varying slowly over time, because then that would bias your measurements. Um, the other cool trick that she used was to take one of those negative plates and make a positive plate out of it, um, and then take the negative plate from, let's say, June and the positive plate from July and overlay them on top of each other and register every star on top of its twin from a month before. If the star had not changed in brightness, then its dot on the plate would not have changed in size. And so if the black dot from the negative plate perfectly covered the white hole in the positive plate, there would be no light coming through the plate from the back. But if the star had gotten bigger or smaller, there would be a ring of light visible around the star that had changed in brightness, or all the stars that had changed in brightness. And the human eye is really good at noticing those little rings of light out of a completely black image. And so this technique was a big time saver. And I was able to attempt something like this. That's my finger, and those are two plates. And there's a star that has greatly changed in brightness over time. This is very hard to do because you have to look straight down through the plate to make the stars line up, because the stars are they're a thickness of glass apart from each other, so there's some parallax to worry about as well. But that's in her lifetime, she discovered over half of all known variable stars during her short tenure at the Harvard College Observatory. And she was tracking over 2,500 of those stars on every plate that came in. And this is kind of what she would have seen. I took this picture through a jeweler's loop that was placed on there, and you can get an idea of how hard that is to do. Only the stars right below the loop were actually lined up carefully. The others are off center, and you have to slide the loop around the whole thing. It saves a lot of time, but it's not easy to do. Um, so she found lots of different patterns of variability among all the stars that she studied. You can see one in the upper left here, just sort of a big trough. Quick dips, fast drops, fast rises, and so on. But out of all of those stars, 2,500 of them, she noticed a small number of them, just 16 stars, had this very unusual pattern. They got bright really fast, and it took them a long time to go down to their minimum brightness. This is 16 stars out of 2,500 that she was careful, bright, and aware enough to see. This, I think, this is what inspired Anna von Mertens to name her book "Attention is Discovery." Uh, Henrietta Leavitt paid very careful attention to the stars that she was studying. And as a result, she was able to notice that these 16 stars had this very unusual pattern. And she called them Cepheid stars. Well, we call them that today. Um, and she noticed something interesting about these 16 stars. And the interesting fact was that the brighter the star was at its peak brightness, the longer it took to dim to its minimum brightness or return to its peak brightness. So here you've got a case of a magnitude 12 star, which is the brightest one on our chart. Remember, the numbers go the wrong way. And a magnitude 12 star in the Magellanic Cloud that had this pattern typically took 40 days or so to return to its peak brightness from its earlier peak brightness. A magnitude 13 star that was a little dimmer than the magnitude 12 star at its peak only took 25 days to get back to the peak brightness. A star that was dimmer than that, magnitude 14, only took 10 days, and a magnitude 15 star took even less than that. So here's a, a time exposure over 41 days of a Cepheid variable star in the modern sky. And you can see in the animation, in the video here, this is not an animation, but a movie of the star's brightness over 41 days. And you can see how it jumps up in brightness very quickly and then takes most of the 41 days to get dim again. And this is this happens when stars are at a certain phase in their life cycle. They puff up and get dim, and then they shrink back down and get brighter again. And this process goes only for a certain portion of their life cycle. So it's not something that
Okay.
happens to every star, and it doesn't happen during its entire life. It's only for a certain portion of the life cycle of stars of a certain size and mass. But here's an example of one that has a 41-day period. And you can see in the movie just how quickly it goes from dim to bright, and then it takes a long time to go from bright to dim. So
Ted,
this is what
uh,
Henrietta
it,
Leavitt was trying to infer from these random pictures at different times during the 41-day period. This is a mental job that takes some real serious concentration.
Hi, Ted.
Um,
We have a question from Mario Mata.
sure.
Ted, I couldn't help but notice, is that a light echo that's seen spreading out from the star?
Good question. I suspect that this is part of the outer atmosphere of the star from when it gets big. That's an actual physical explosion
Yeah, no,
of the
I
outer layers.
certainly the gases. What I'm
Uh,
asking is that a light echo reflecting off the light, off the surrounding gas nebula?
yes, it probably would be, depending on how long, yeah, how long those earlier explosions were now from the star. So yeah, after a certain amount of time, you would get an echo reflecting off of the those gaseous emissions. Yes,
That's a great
absolutely.
example then of a light echo.
Yeah, pretty cool. Thanks, Hubble. So we talked about, she was not trying to understand how far away, how big the universe was, but she did ask, the question, how do I know that the brightness values of my stars aren't being affected by distance? As we said earlier, a bright star that's far away can look really dim, and a dim star that's close can look much brighter than that intrinsically bright or large star that's far away. But as I mentioned earlier, she had the simplifying assumption all of her stars were in the same Magellanic Cloud, and so she could safely assume that they were all about the same distance away. So one of the variables was controlled, the actual distance to the stars. She could assume that all these stars were close to the same distance from us. So that was a simplifying assumption. So in the bottom of this page is the statement that she made in an article that was published by Edward Pickering. But you'll notice that the first statement in his published paper says the following statement regarding the periods of 25 variable stars in the small Magellanic Cloud has been prepared by Miss Leavitt. It was absolutely unheard of to give credit to these women, to the computers who were doing these calculations, but he understood that she had made a great discovery because she said, since the variables are probably at nearly the same distance from Earth, their time period between brightness to brightness are apparently associated with their actual emission of light. And so she drew this graph of the apparent magnitude of the star along the vertical axis and the period of star in days along the horizontal axis. And there did seem to be a relationship, but when she graphed that on log paper, we have a classic case of a straight line relationship, saying that there's a relationship between how bright the star is at its brightest and its period between peak brightnesses. That's an interesting relationship. Can we make something out of that? Can we take advantage of that in some way to maybe solve the question of how far away are those nebulous objects? Are they in our galaxy? Are they outside the galaxy? Are they independent, distant galaxies? Well, let's understand that the key that Henrietta Leavitt understood was that unlike most stars, which only send us information about their brightness by their brightness, which we know we can't trust, these stars were sending us information, the same information, two different ways. The first way was how bright they were. And we know already that we can't count on that to tell us how far away the star is. I mean, Deneb and Altair are about the same brightness in the sky, and they're like 400. Deneb is like 400 times farther away. So it's enormously brighter intrinsically from the same distance as Altair, but you can't tell that from looking at them. But the second way that the stars were telling us something about their brightness was the time between the peak brightness activity. And the time between the peaks is independent of how far away the star is. I mean, if you're getting a newspaper from Britain on a ship, whether it takes a month, 6 months, or a year for the news to get to you, the newspaper still has the same news in it. And in the same way here, the time between the peaks that's coming to us at the speed of light may take a long time to get here, but when the two peaks get here, they're still the same amount of time apart as they were when they left the star. So the time between peaks is independent of how far away the star is. And that's the key to Henrietta Leavitt's discovery here. So remember algebra, right? If A equals B, then B equals A. And so we have two relationships here. If we know the maximum brightness of a Cepheid star, one of these 16 stars that has this same pattern, using the blue line, we can see what its maximum brightness is, go over to the line, and then go straight down, and you can say what its period should be. And it matches up for those 16 stars. But since A equals B, then B equals A, you can also use the same graph in the opposite direction, right? You can say if it has a certain period in days, then you can go up to the graph and you can say, Well, how bright should it be if it's the same distance away as all the stars in the Magellanic Cloud? This is the way we're going to use that time difference peak to peak, which is invariant depending on distance. Brightness we can't use, but the time difference between peak to peak is independent of distance. And so that's what lets us start at the bottom of this graph, find the period of a star that we're observing, and then go up to the line, go over to the left, and say, if this star was a Cepheid variable and the same distance away as the Magellanic Clouds, it should be, in this case, magnitude 12.5, roughly. So this is the key to everything. So this is one thing that she could now say. Any Cepheid variable star with a period of, say, 40 days that was at the distance of the small Magellanic Cloud should have a peak brightness of about magnitude 12, because all the stars that she saw that had a period of 40 days in the Magellanic Cloud, peak brightness was about magnitude 12. If they had a shorter period, they had a dimmer maximum brightness. So we've got this relationship. If it's 40 days and it's one Magellanic Cloud unit away, its peak magnitude will be 12. So let's pose this question, right? We've got this relationship. If it's a 40-day period and it's the same distance away as the Magellanic Cloud and it's a magnitude 12, then if you found a Cepheid variable in another part of the sky with a period of 40 days, but its peak brightness was much brighter than predicted, would that star be farther away or closer than the Magellanic Clouds? Remember, it's brighter than it should be. So
Closer.
it would be closer, exactly, than the stars in the Magellanic Cloud. Because if it was in the Magellanic Cloud, it should be magnitude 12. But this star, let's imagine, is magnitude 9, say, about 10 times brighter. So it must be closer, because we know its peak brightness is the same as other 40-day stars that are in the Magellanic Cloud. All right, closer, right answer. So one more question. Again, we found a Cepheid variable in another part of the sky. It's got a period of 40 days, but its peak brightness is much dimmer than magnitude 12. It obviously has to be much farther away than the stars in the Magellanic Cloud that were magnitude 12 with a 40-day period. So again, here we're using the time difference between peaks as an independent measurement of how bright the star should look to us at a given distance, the Magellanic Cloud distance. We don't know how far away the Magellanic Clouds are, but we're just using that distance as one unit, like one astronomical unit, the distance to the sun. So this is a Magellanic unit, the distance to the Magellanic Cloud. We don't know what the mileage is, but let's just take that as a measurement, one unit. Okay, so between 1925 and 1929, Edwin Hubble starts using I think the 100-inch telescope to look at the Andromeda Nebula. He resolves it into stars. Now he knows it's not a ball of gas, but it's billions and billions of stars. And he sees in that plate what originally he thinks is a nova, a new star. But by taking multiple plates over time, he crosses that N out and puts a different word on there. He says it's a variable star, and he uses the exclamation point because he's discovered that it's actually a Cepheid variable star, the kind of star that follows the Leavitt law that he knows about. By this time, Henrietta Leavitt has passed away from stomach cancer, but astronomers, including Edwin Hubble, know her relationship very well. So here's the graph of that particular star that he publishes. In fact, he sends this curve to Harlow Shapley, who Harlow Shapley was an advocate of the universe being the entire Milky Way, or the other way around, the Milky Way being the whole universe. So everything, including the Andromeda Nebula, would be right inside our universe, and we're the whole universe. The all the little fuzzy objects, the Stephan's quintet, everything are all part of our universe. There's nothing but the Milky Way in the universe. We're it. But Shapley read this letter and said, "This is the letter that destroyed my universe," because he understood that Hubble had found a Cepheid variable in the Andromeda Nebula, and it was a period of 31.4 days. So he took Henrietta Leavitt's graph and he said, okay, it's 31.4 days. By Leavitt's law, if that star in the nebula was the same distance away as the stars in the Magellanic Cloud, it should have a peak brightness of about 12.5, because all the stars with 31-day periods in the Magellanic Cloud had a period of about a maximum brightness of about 12.5. But this star has a peak magnitude of 18.2. It's 250 times dimmer than a 31-day period star should be if it's at the distance of the Magellanic Clouds. So the only thing that can be the case is that this star must be much farther away than the Magellanic Cloud. And in fact, it has to be 15 times farther away than the Magellanic Clouds are to be 250 times dimmer than it should be. That is way outside anybody's estimate of the size of the Milky Way. And that's why Harlow Shapley said, this is the letter that destroyed my universe. So by following Leavitt's law, he was able to show that the Magellanic Clouds were not only outside the Milky Way, but the Andromeda Galaxy, Andromeda Nebula, was in fact an island universe, a separate galaxy from our galaxy. I think this slide is supposed to have an animation on it anyway, showing the Andromeda Galaxy moving farther and farther away. The Andromeda Galaxy is 25 times the Milky Way diameter away from us, with nothing in between but empty space. So anyway, Delta Cephei, which is the star we pointed out as an example Cepheid variable, has a 10-day period. It was determined by parallax to be 850 light years away. And so we now know that the Magellanic Clouds are actually about 150,000 light years from us. The Milky Way is about 100,000 light years across. So they're 40 to 50,000 light years outside the Milky Way. Definitely not part of the Milky Way. Very close, though. I mean, they're 40,000 light years away, and the Andromeda Galaxy is 2.5 million light years away. But both of them are slightly outside. But luckily, they were present. They had enough variable stars in them for Henrietta Leavitt to do her work and make her discovery. She was actually nominated for the Nobel Prize, but by the time someone came and inquired about her, she had passed away, and Nobel is only awarded to people who are alive. Here's our little animation showing how far away the Andromeda Nebula actually became as a result of Henrietta Leavitt's discovery and Edwin Hubble's use of the Leavitt's law to do that, about 2.5 million light years away. And now we know that all these little objects in the Hubble Deep Field are in fact island universes or galaxies like ours with hundreds of billions of stars, lots of planets obviously around them, and who knows, potential for life as well. So she was the first to measure the universe. She was a lovely person, died in 1921. That's her gravestone in Cambridge. And people wrote wonderful things about her at her eulogies and so on. Here's a picture. This is one of the bulletin boards at the Harvard College Observatory plate stacks, and you can see Edward Pickering there, Annie Jump Cannon on the left, the plate stacks, and Henrietta Leavitt. And I think Cecilia Payne-Gaposchkin is on there as well. So the three most famous of Pickering's harem, who became very famous in their own right. This is the book that got me first interested in Henrietta Leavitt's stories. Miss Leavitt's Stars by George Johnson. It's a little paperback. And then Davis Sobel wrote her really great book, The Glass Universe, How the Ladies of Harvard Observatory Took the Measure of the Stars. And this is the story of all of those women. Um, and then here is Anna von Merten's book, Attention is Discovery. It's a coffee table size book. Beautiful, beautiful stuff. And she's a quilter, so she actually made quilts of many of Henrietta Leavitt's photographs and has done displays of her artwork in universities and art galleries around the country. So she's an acclaimed artist. And then she wrote this book about her project uh, about Henrietta Leavitt. And there's a children's book as well by Raul Colon, um, Henrietta Leavitt, pioneering woman astronomer. So lots of that. So I'll close with the this is the final scene from Silent Sky, the play, with Henrietta Leavitt looking through one of her glass plates, and they do a great job of documenting and explaining the story. It's very inspiring, and it does bring it down to earth for folks without a lot of astronomical knowledge. Um, so thanks to you all for listening, and thanks to the Harvard College Observatory, to Allison Doan, who brought me in and handed me a copy of Henrietta Leavitt's notebooks and said, here you go, take some pictures of it. And of course, my friend David and the Dash Project. So I'm open to questions if you have those. We'll stop sharing now and see if we have any questions.
Thank you very much.
Uh,
You're welcome.
You're all welcome to unmute, and we have questions already. I'm going to start with Irene.
Hi there, and thank you very much. My God, that was fascinating. In our club down south, we've learned how exoplanets have been discovered, and one of them is photometry, I believe is the word, spectrometry, and they use the dip in the brightness to determine that a planet might be passing by. So, of these variable stars, how do we know that some of those light changes aren't due to a passing planet or no other?
That's a good question. For a uniform dip in the brightness of a star, you could postulate that a planet passing in front of it could cause that dip in brightness. But for a variable star that has a pattern like our Cepheid variable, where the brightness the change from dimmest to bright is fast, and then the change from bright to dim is slow, that's not possible to be from a single body passing in front of the star.
Yeah, I thought that looked bizarre. Yeah, but there was one
So
dip that looked like it was just very quick and then went up again. So, but
yeah, that would be unique. But yeah, uniform changes in the brightness, you have to measure. I'm not sure how you would disentangle one from the other. I hadn't thought of that, but you're right. There's a confounding effect there, and you'd have two possible sources for that to happen.
Thank you so much. Great.
Mario?
Yeah, I just want to let people know that the play was available at the Central Square Theater in Cambridge. In fact, I saw it there with my wife a few years ago, and every couple of years they bring it up again. So unfortunately, it just ended.
Oh no.
Well, it was running since early September, but you can contact the theater, and they seem to bring it back every 2 or 3 years.
Mhm.
So, and real question though is, did you ever finish that planetarium?
Well, actually, we finished the observatory
Ah,
at the other end of the building, and just 2 weeks ago, we installed the CDK 700 plane wave 27.5 inch scope. And I have looked through it. I have taken
27
photographs
inch
through
plane
it.
wave?
27.5 inch plane wave.
Wow, I didn't know they made them that big.
Yep. And there's a tertiary mirror in it that's on a motor. So we have a camera port, a Perseus port selector on one side with 4 cameras on it. And on the other axis, there's a periscope that brings the image down to eye level. So the scope is up high, but the periscope is 6 feet long. And the periscope is made up of two Teleview NP101 IS scopes, nose to nose.
They did
Either
that
one
with
of
the
those,
hooker.
Either of
They
those
do
would.
that with the Hooker 100-inch.
Oh, do they?
Yeah,
Well,
I looked through it a couple of years back, and they have this like periscope thing. You stand on the ground, and people can look
exactly.
through the
Right.
telescope.
So as the scope spins around, you have to be careful that the periscope doesn't knock you over. We have some stanchions around it, like at an airport, to keep you out of trouble. But it's not open to the public yet. But we just got funding for the planetarium at the other end of the building.
Yeah.
And so we're in the process of, we just got a bid for that. And that's going to have a 40-foot, 12-meter dome and tilted dome and 65 seats. And that should be open in by next summer. Right now, it's a dome with insulation under it. It's completely unfinished, but it's
Well,
dried in and ready for the dome people to come in and do
that's
their
great,
thing.
Ted. I'm coming out to Arizona March 3rd. David Levy and I are going to Mount Palomar to image the lunar eclipse
Uh-huh.
with the director of the Palomar Observatory. And I have grandkids now in northern Phoenix area,
Oh,
so I'd like to come over and see that if I could.
absolutely. Just let me know when you're going to be in town. We'll make
Okay, the
sure we
first
get it.
week of March.
You and David can come together, bring the grandkids, and we'll give you a nice tour. Sure.
Okay, send me
Absolutely.
an email. Okay.
Will do.
Any other questions? Okay, I don't know who this person is. Karante Space.
Nice to meet you. Let me introduce myself. I'm Jose Angel Mora. Jose Angel Mora Robles from San Cristobal, Venezuela. I'm very, very pleased. Ted, thanks a lot. Um, uh, uh, Henrietta Leavitt was one of my heroines. I worked with her in my graduate thesis because I was studying how the conscience of the people in the earth changed along the times from an heliocentric universe, from an heliocentric universe, an acentric universe. Now,
Hmm.
after Elvin Hubble, she noticed that they are far away. So see, they are expanding, they are running when they start to run. So they turn the clock back. I found that justamente just the time 40 million years ago. So now, thanks to Henrietta Leavitt, we know we have an expanding universe, because also it's the untold history about photography, because near and at the beginning of the 20th century, the photographic camera replaced the astronomer eye at the end of the telescope. So
Hmm.
all the discoveries, but all the findings was made um, by the means of photography. So photography was the hidden star behind the backstage, but was photography the tool, the technological tool to made possible to measure the universe. Without photography, we surely we haven't found the way to measure the universe. Thanks a
Absolutely
lot for
agree.
your
Yeah,
time.
there would have been no way for her to visually observe the changes in brightness of these stars over time. No human brain and eye could possibly have remembered the brightness from last week or last month or last or yesterday and say, "Oh yeah, this is brighter." The only way that the AAVSO folks do it, of course, is by being told that here's a star that never changes brightness. Now you can compare the star that's variable to all of these other stars around it, and that will give you an idea of what to report for the current brightness of the variable star. So yeah, photography is really important unless you've got a map of the non-variable stars, like the AAVSO provides you to make a comparison. But to make those, you need photography to start with. So yes.
Yes.
So I just want to
Hi.
note, I just want to note that our guest from Venezuela uh, represents the National Astronomy Education Coordinators uh, in Venezuela, which is part of a large network put together by the International Astronomical Union. Is that correct?
Yes, yes. Since 1924 until 27, I'm working as a National Astronomy Education Coordinator in Venezuela.
That's awesome. So yeah,
Wow.
great
Nice
to
to meet
have you
you.
here.
Mhm.
I do have a question having to do with the provocative phrase silent sky. And you've already mentioned that Henrietta Leavitt became deaf in her later years. So my first question is, how late did that happen? And then my other question is, there was another computer or calculator at Harvard who was deaf. And I was wondering if you had any insights about that.
Mm. Uh, I think her deafness lasted for about the last 10 years of her life,
She was 53 when she died.
but I don't know about other folks who worked there who were hard of hearing. Yeah, sorry, I don't have an answer to that one.
I guess it's something which could be found in by Googling it.
I
Uh,
think in Davis O'Bell's book, she postulates that uh, she found that her lack of ability to hear actually allowed her to concentrate better on the
mm,
work that she was doing.
mm.
Mhm.
That's very painstaking work, as you said.
Mm.
Just amazing.
Mhm.
Ted,
There is
what
also, but go ahead, Michelle.
Oh, hi. Yes, thanks for the talk. Very good, very interesting. Um, she um, she invented for the first time a method to calculate the distances. But it looks to me that there is a big margin of error when you calculate a distance based on that method. Then can you give us an idea of how much error is involved?
Not really, but I do know that after she published her work and Hubble used her Leavitt's law,
Mhm.
um,
Yes.
Harlow Shapley discovered that there were actually two families of Cepheid variables,
Ah, mm,
and that by averaging the two families together as she did without being aware that there were two different patterns, Leavitt's law was not as accurate as it could be, and there was some confusion. But eventually, when he discovered that there were two types of Cepheid variables, and you could separate them, the errors in the estimates got smaller
mhm,
because now you didn't have this mixture of two different types of variables that you didn't understand.
mhm,
But I don't know offhand percentage wise what the confidence intervals would be, what the uncertainty would be for using this technique. Obviously, I see today, I see star magnitudes reported to 100th of a magnitude, and I find
oh,
that absolutely unbelievable. Obviously, it's being done with photometry and counting photons and so on, but she did it with, looking at a plate that was developed, who knows at what temperature and who knows for how long. And there were so many variables that, the
yeah.
fact that she actually was able to identify stars to a tenth of a magnitude, I thought was unbelievable.
Mhm.
Mhm. Thank you.
Um, I
Miss Levitt had
wanted,
absolutely no control of the telescope or the photography that was being done. She was just given access to the plates, and she did this because she could use the plates to view what was going on. But she never, I wonder what she would have accomplished if she could have actually had any control over what they were photographing and what,
Right.
how they did it. Just
Yeah.
astonishing what was accomplished.
when I was able to enter the logbook from the Bruce telescope for 1 month, I think it was, maybe 1 year, I can't remember, but there were lots of notations like uh, the weight from the clock drive hit the floor in the middle of the 15-minute exposure, and so
Oh.
this one's no good. And
Whoops.
you just read those things. Clouds came in, it started to rain, we had to close the dome. It really brought you down to the observatory overnight time that these folks were operating these machines at a very basic level compared to what we have today.
Yeah, it's very primitive having to manually do everything. And now
Yeah,
it's all push a button, let the computer run it for the next 6 hours. Um, I'm just
exactly.
astonished. And thank you very much for your presentation. That was delightful and
Thank
very
you.
informative.
Thanks so much.
Before we get Mario's question, I just want to note that it was Annie Jump Cannon who was also deaf.
Well, okay. Thank you.
All right, Mario.
Yeah, I just want to let Ted know. I About 12 years ago, the AVSO had a project as requested by Johns Hopkins that controls the Hubble for us to recalibrate variable one. So I actually have images of V1 at its peak and at its minimum in my files, uh, which was submitted through the AVSO. And then the Hubble team wanted to take, in honor of Edward Hubble, they took pictures of V1 with the Hubble telescope. But if you'd like a peak and minus taken through my 32, I have them and you can use them in your talks.
Thank you. That would be great.
Yeah,
Yeah.
let me know.
Yeah, appreciate it. That just to see them at to see that star at its different brightnesses would add a lot to the talk. So thanks. That
Yeah,
would be
I mean,
awesome.
in my image, you can tell which star is changing because it's pointed out. But you couldn't do that real time, obviously.
All right. Thanks. That'd be great. Appreciate it.
Well, that was wonderful. Um, and I want to note your opening slide sort of said NASA Solar System Ambassador, but you actually did
Now,
an anagram. Is that what it was?
well, because of the shutdown, those of us who are those of us who are solar system ambassadors are we're asked not to kind of advertise our our status in order to avoid giving anyone the impression that we were spending money, that even though solar system ambassadors don't get paid. So you can see here that I created an anagram of NASA Solar System Ambassador so that none of you would know that I was a NASA Solar System Ambassador. As, so I'm trying to follow the rules here.
I think you did a bang up job.
So just keep it on the quiet side here.
Okay, excellent.
No
Well,
one will
thank
ever
you so
know.
much, Ted.
You're
Uh,
welcome.
your contribution gives great heft and value to the something Maynard Albatross or whatever it was. What a great organization.
Yeah, there the albatrosses. Samosas are delicious too.
Samosas.
Yeah.
Okay, I think we'll call it quits here.
Thanks,
Thank you
Bill.
all for coming.
Thank
Great.
you all.
Cool.
Appreciate it.
Have a
Take
great
care.
Wonderful.
night.
Bye-bye.
Have a great weekend.
Bill, as always, thank you for inviting me.
Oh,
See you next month.
I rely on you, Patty.
I'll never let you down.
Thank
God
you.
will.
Thanks a lot.
Yeah. So long.
Bye, everybody.
Thank
Bye,
you.
everybody.
Bye.